It's time to start our conference, and the first speaker of today is Markus's PhD advisor from a few years ago. Martin Schottenloher from Munich University will talk about geometric quantization, a mathematical path to quantum models.
Yeah, thank you and good morning. First of all, I want to thank the organizers for inviting me so I can give a contribution to this conference in honor of Markus. So this is what is really good. In fact, I know Markus for quite a while. About 30 years ago, you can say, we discussed and even worked a little bit on general questions about quantization, how to get quantum models out of classical models, and at that time we even wrote a paper together. But today I want to give a survey in geometric quantization. Geometric quantization tries to get quantum models you can say these are the set of our quantum models, whatever that is. I will try to explain it a little bit later. And out of classical models, I will explain this also in detail. And the question is how to get quantum models out of classical models. This is not really something physical in the sense that there is a physical principle who would tell you how to do that. There's nothing like that, as at least to my information. It's just the possibility to get good quantum models in any way. If you have a good idea of a quantum model without construction, of course, that's nice. But sometimes the construction can help to find new models, or rather, at least can confirm that this is a good model and so on. So the point is here, the methods in geometric quantization are geometrical and of course mathematical, and I may be allowed to say rigorous mathematics, because in physics there are some not principles, but some methods to get such models by canonical quantization, for example, and this is really rigorous mathematics. So let me try to define these two subsets, or these two models. The simple classical model is, for example, the harmonic oscillator. In this case, you have it as a phase space. You take these are Rn, the cotangent bundle, which is essentially the same as Rm cross Rn. Rn is the configuration space, and you have moments also. And you can say this is the contraction coordinate, this is the momentum coordinate. In one coordinate or n coordinates, you can see it as a vector. And what you have is the harmonic oscillator, the energy function, which is also the function which essentially generates the evolution, is this h, and the evolution itself is given by q point equals p and p point equals minus q. So this is a very simple model, but it's already interesting also for our general question. And before I give that's really heavy. Before I give the general definition, I talk about quantum models. in some sense they are simpler in our context, although quantum mechanics is not simpler than classical mechanics. But here we have only to have a Hilbert space. We denote the operators on Hilbert space, and these are a set of self-adjoint operators, which are not necessarily bounded. And we have more or less one, how to say, let me call it, it's not this age in general, but in a special example. One example of, you have one operator fixed, which is responsible for the evolution, and you have some more which give you quantum observables. And the evolution is I times h bar, and psi is a general wave function in h that equals, sorry, this is the evolution. And so these examples look easy, but if it comes to physics, only the eigenvalues are really relevant because you had the chance to measure them and so on and so on. So, but I don't go into physics. We are here in mathematics, but constructing. So let me get the general definition of the classical model. I restrict here to Hamiltonian mechanics, and the general case is the phase space is the symplectic manifold. So M is a manifold, 2n dimensional, and omega is a two form. The symplectic form, and omega has the properties that omega is closed and non-degenerated. So this is a very general definition, but we need this, in fact, in classical mechanics and also then for the construction, because many phase spaces are, in fact, not as easy as this situation. And it comes already to complicated phase spaces if we look at reduction. Reduction in classical mechanics is a very important point, and in some sense, only because of reduction you can really solve problems in classical mechanics. And the reduction simply says that we, first of all, we have here, for example, n variables or 2n variables, in fact. And in particular, in this case, you can say h is an invariant of motion. And this means that if we fix an energy E, so the example above, if we fix an energy E, then we can look at the energy surface, which is in fact a sphere in r to the power 2m, and we know that if we have fixed the energy, then the whole evolution happens in here. But also because it's, I mean, if you change a point looking at it as a complex variable and you change it by e to the power it, then this is also the same situation. And so you can look at the orbits with respect to the motions of h, and we get here s to the power n plus 1 over a certain, over this equivalence relation, and this is nothing else than the projector space over C. And this is a really more complicated space. In fact, even the first steps of geometric quantization cannot cover this case for some reasons. which lie in the topology of Pm, because a certain Chern number is not divisible by 2. In particular, the Chern number of this is n plus 1, and if n is odd, then n plus 1 seems to be even, and then this is good. But if n is even, then n plus 1 is part, and then we had a problem with the Chern numbers. But this is just unimportant for those who don't know what Chern numbers are. It just stays or hints that even in this very, very simple case, the mixed step is already complicated. And of course, we are much more interesting reductions. For example, the two-body problem, if you start with it and again factor out with the energy number E, then the resulting space is S2 cross S2, which is, of course, looking very nice if you want to imagine what it is. But it is a more complicated space. It's a general cotangent bundle. Okay. So what? This is just the model space. What happens in the symplectic manifold? First of all, you can for f a general function on M. A general function from E is a differentiable function, and the following all the time. We can define the so-called Hamiltonian vector field with respect to xf, and this is essentially in canonical coordinates is df. So now I am always a little bit confused because it is general in symplectic geometry and also in physics. The two variables are sometimes changed, but I think this or the minus of this is correct. And this is the Hamiltonian vector field, and it is nice if you look, for example, at our first example, the two form above there is not maybe mentioned, but if we mention it now, then we can define in canonical coordinates this xf is independent of the canonical coordinates, and it says that the qp point, if you now take a point in the free space itself, then this is x of h qp of this h. And this is in general the evolution equation in symplectic manifolds when we look at them as phase spaces. And another thing should be mentioned, the Poisson bracket of two of these observables is defined to be omega of xf xg. And although I had used coordinates here, these definitions are all invariant against coordinates. They are really intrinsically defined and can be done a bit more complicated. So now we know what a symplectic manifold is, and let me now explains the problem we have to solve. Given x omega and a couple of observables em which are interesting for us, they will be taken normally as Lie subalgebra of this Poisson algebra, and we want to find or construct H a Hilbert space and Q a mapping from, you can say R, to the operators of a page, such that Q is linear, and we have two conditions which I call D1 and D2, because they are all very often called the Dirac conditions, and the interesting point is that they had been defined by Dirac about 100 years ago. It's interesting that Markus at the very first moment one had already this picture and a Q of 1, so we always want to have 1 inside, should be 1, and the commutator of two of the operators, I call them quantum operators, related to F and G, they satisfy the following equation, which is very close to being a representation. And that here we have the Poisson bracket of the two functions f and g. What I did here is I identified h with 1 to make formulas a little bit easier. And because the whole construction does not depend in any sense on the Planck constant. But of course, at the very end, you can plug it in again, and then you would have here I of h bar. Okay, these are the quantum conditions, and let me try to show how the physicists do it, or what physicists, some in the very first examples have been given by this. Namely, first of all, we are more or less in this situation, or slightly different, slightly more general. The Hilbert space is the L2 space of Rn, and I call it Q of little q is, let me write it down. Psi is now a function on RL, the wave function, multiplied by Q psi, but okay, I should now really look at coordinates to make it more sensible. Otherwise, all the formulas I write down without indices can be understood at least for one degree of freedom. So for can equal 1, and P of pk is essentially the derivative, and here we need a certain constant in order to make it really for h. This is okay. And now the canonical quantization, of course, has several definitions. Like one way one could say it is the following: if we have a general,
it's P. It's not P. It can Q. Not left. Was that? So Q little left. It's Q of the capital Q. It's instead of
okay. Are you all right?
and then this
Okay.
Yeah. This is good.
All right.
So
At the end, I wanted to call this Q and this P, but this is a better sense of our situation there. And so this is a classical variable, and to make it the quantum variable, the quantum operator, we replace Q k by Q k, Q k, and I had an upper index by Q of P. And so my leading example, a harmonic oscillator, we see that Q of H is very nicely 1/2 Q. Now it becomes complicated. Let me write it this way. Q is Q1. Oh, Q1, I changed my and P is PQ, P1 up to PN. So, and this is just spectrum multiplication, or just multiplication. So this is, what it is here we have a certain other constant. I don't want to calculate because I would make it wrongly anyway. And this is essentially a constant times the plus operator. And this is what really the harmonic oscillator operation is. This is a very simple example. And if you're a physicist, you're certainly happy. As a mathematician, you like it too. But this doesn't work always, because what shall we do with the case F equals P times Q? And here you see it will replace. We have to give an order, because first, let me now use this example. P times Q is certainly something different than MP, so we don't know what to do. We are at the end of the story, but of course, if one looks at examples, then one sees it's a very good choices to just more or less take both, but and the half of it, and this is in some sense. So this is canonical quantization that you replace in this way, but if something goes wrong, you might have to invent a new rule, and there are examples where this is not correct. And so, canonical quantization is not a strictly mathematical principle that you can say. To what geometric quantization does differently is now to make it more rigorous, and of course it becomes more complicated. So my mathematics is mostly it's too complicated for physicists because it's not so easy to handle. One fact I want to use, and this is still coming from the classical models, and this is that forming the Hamiltonian. So F goes over to XF. This is the mapping from the Poisson algebra into the algebra functions, operators, algebra in the sense that you can use a commutator, although it's a bit difficult. It's not really an algebra, it's more complicated. But in any way, what is true is, if we take the commutator of the two vector fields, then this is nearly the same as the commutator of the Poisson bracket. It's just the minus here. The minus is not important, and but you can say this minus is responsible for this minus in some sense, and So, but this is a good hint. The Q we are looking for in mathematics or in physics is somehow related to XF. And if we want to emphasize that XF operates on E, then we sometimes write it as a Lie derivative, but it's exactly the same. You know, xf of any wave function is the same as Lxf of any wave function. So this is a good candidate for further investigations. And in fact, we are now at the first stage. We are now at the first stage of of geometric quantization, and this is called the so-called pre-quantization. It says already that we are not at the end of the story, but it's the first step. And so if we take QF equals LXF, then we see that, okay, we don't discuss the linearity, whatever we write down is linear anyway. So it's not really a big condition above, but fulfills D2. I mean, that, well, it's not quite true. I have to get. So because of this rule, I mentioned as a fact, and by the right constant here, we have D2, but not D1. That's easy, but we are close because D2 looks more difficult than the first condition. So what we do is we replace, or we add the constant, or you can say the multiplication with f, and this fulfills dot. This goes wrong, but D2 is fulfilled. So 2 tries, so we always have a third try, and what we do, we correct this picture by an expression alpha xf, and alpha is the one form. Okay, I make this more or less in all the time by looking either at T star of R end with our omega in this example, or we require for a moment that there's a potential for omega, a global potential, which is not the case in general. But if that is true, then we can make this assumption. And yeah, now you can say the big proposition, but it's not difficult to show if the, okay, let me call it this Q prime f and this QF. Q and then this new Q satisfies D2 and D1 exactly when D alpha is already omega. So I use it here in order to define it. Looks a bit weird. So, but anyway, for this case, one can see that the condition that this is true has to be D alpha is equal omega, and we have assumed it anyway. In general, one can do this only locally in open sets, which are charts of the manifold, and then alpha has to be a local potential of omega, and this gives you. So I don't want to write it all down, which is lengthy. This is at least true locally, so we can define such a global. The global thing is then well defined because we have each time the two alphas in an intersection of a chart agree because the d alpha is omega essential. They agree up to the constant, and this is of no importance. So at the very end, we see locally, yeah, And now we make a little gap. People, physicists who work with gauge theory and gauge potentials and so on, if they see something like this is true locally, at least. You know, the theorem or the proposition would say that if we have local potentials, then we have to have them be local potentials of omega. And the physicist sees immediately, and mathematician who does geometry of vector fields sees also there should exist a complex line bundle with connection or Fourier derivative, such that the local potentials satisfy this, or such that such that the curvature of L with this covariant derivative is exactly omega. So this is a gap. A line bundle, that explains everything about line bundles, and the lecture would be over. So please, who does not know what a line bundle is, would somehow accept that this is a general situation. A very, in our trivial cases, a line bundle would look like the product L, and locally it looks exactly like that, and we have to draw them together over charts to make it sensible. Okay, this is this is non and with Egypt, thank you. Okay. Now the main result you can say in pre-quantization is the following. Given M a classical phase space and a complex line bundle, L over M. Okay, we have over M here. This means we have a mapping from L to M pi, such the fibers of pi are exactly Cn, C1. This is a line bundle. Over each point we have exactly one line. Over M with a so-called Hermitian connection. This is not very important at the moment. Del or nabla, such that the curvature of this is omega, then Q have times minus I over 2 pi. Yeah, and now we replace you can say the flat connection, which is L x, we replace this by nabla of xf, thus f. This operator Q now from all of the EM to the operators of H fulfill E1 and E2. This is not difficult to write down. It's more or less everything is simple except for the notion of a line bundle. And I will not prove it here. It's a bit tedious. Okay. What it says, yeah, now comes a high point of my talk. The other high points I will not recover anymore because of the sign. the high point is the Pulley. There is a theorem of Weil, Andre Weil. Not the other Weil, there's another one Y. and it says Hell Mabler exists in this context if and only if omega is integral. An integral as a cohomology element of the arm cohomology, for example, or one can give it in physics, or not in physics, in geometric terms. You can write it, sometimes it's the same for the mathematics, but this is an integer for all S surfaces in the sense they should be compact and oriented without boundary. No boundary. Anyway, if you say surfaces, this is meant anyway. So this is very interesting that we have this integration is always an integer number, or this is an integral cohomology class, and this says it's a quantum condition. And insofar I meant condition. Insofar I meant this is a high point, because it says this works only if the original manifold together with its omega, with its symplectic form, has to fulfill an integrality condition. This is also very often called integrality condition. And let me just mention with one word, I don't write it down because it will take too much time, but here we have all classical observables, which is a bit weird because we know because of other reasons that a good quantization does not work for all classical variables at the same time. There's a no-go theorem. And also, let me mention that this can be made better, but it doesn't help because it's not so good anyway. That to a Hilbert space, because what we do is we use Hermitian, and then we can integrate over omega to the power n. This is a 2n form and non-degenerated, and we get a Hilbert space. And two of with respect to this. Okay, this is not so interesting because the good thing is we know already that we have restrict our our classical models to get good things. But the bad thing is that this space has too many variables, or better to say, the wave function have too many variables, and one should somehow cut down. So too many variables. For example, in our leading example, the wave functions which depend on QP should depend on CQ. So what we have to have is that we restrict to those functions which depend on the second variable. And of course, this is done in canonical quantization, but here we have to make general principle, and so this comes to the second stage of geometric quantization is to use polarizations. Polarizations I will only restrict to so-called real polarizations. The complex are needed and a bit more complicated, but the general idea can be given by real polarizations. There are so-called distributions, but not in the sense of Lorentz-Schwarz, but distributions are vector bundles of dimension n. and with the property that they are integrable. So I need some.
Can I ask a quick question before you move the chalkboard? Can I ask a quick question before you move the chalkboard? Does this hold for any Keeler manifold, or is it this d alpha equals omega condition? Does that mean that you need to have but does this theorem here?
Yeah.
It looks like if you're saying, like, for instance, if you took your symplectic form to come from just you have a Keeler manifold, a complex Keeler manifold.
No, it's not necessarily Keeler.
I'm just saying if you were to take it, this would hold for any complex Keeler. Is that correct? But I'm confused because on the other side there's the d-alpha
There's an Keeler, or there's a Keeler. This property is not that side for Keeler in general. Of course, Keeler, I mean, this I should have said, and I wanted to say it, that in some sense you can everything you can restrict to Keeler manifolds, because a symplectic manifold in general is already almost complex. It has many almost complex structures, and then to require integrability is something easy. And even from the physical point of view, you could say, I'm not interested in the non-integrable ones, and we discuss all the time in Keeler manifolds. The key one to okay, great.
And then just sorry, is this condition on d alpha equals omega that's a Lobo condition, or is that on the left side?
Here,
because that should put some condition on the topology of the manifold, right? Everybody, I'll come up.
The topology. We need the topology here. Yeah. Okay.
And why you erase the blackboard? Isn't this condition, the integrality, also a reflection of the old Bohr quantization?
You can say for some of the condition, you can somehow reformulate it, and it is exactly the word some of the condition. Very good, interesting, yeah. So second stage. So what we have to have, it is integrable if for all points a0 in M there exists a submanifold or n of dimension n, such that Na is equal to dA all the time. Yeah, it's in the neighborhood here. It's n should be in the neighborhood. But so what it says, it is the distribution. Okay, this is more I can't say at the moment. And what can be done now is, instead of, okay, I haven't said it so explicitly, I see, in my main result, of course, the coup, so let me add it, otherwise it's not complete. Where is it? The result, here, sorry. The result here. This was not good here. I'm very sorry. I should have said the sections of the Mac of this. Many assumed this already because I did everything for the section. So instead of wave functions on M itself, we keep the sections, and the sections are all of M such that we should take this group, the pi cross S to M, and then pi to this L, when we get the identity. These are the sections, and the sections are slightly generalized to functions, you can say, and for them all this is correct. I'm sorry to them for that. And here it says the main idea, and it works quite nice. We take not all sections, but those which are parallel to the distribution, you can say, for all x in D. And these are called the polarized section. And the same can be done for complex polarization, whatever that is. And it is much more general then, and gives more examples. And the nice point is that we can try everything again. And you can say that the first message was pre-quantization works if and only a condition is satisfied. If this condition is satisfied, you can say cutting down my polarizations works. But we are not. It's always the same in geometric quantization. You have a problem. You suggest a solution, and the solution is quite nice at the first moment, and then you are not happy because something goes wrong. What goes wrong here is, problems. What goes wrong, or it's not really wrong. There's no measure easily available. Of course, if you restrict to Kähler manifolds, what you suggested, then this is better. Kähler case is okay, but no matter one has to do some work. This is done by so-called densities. Densities in a very general sense, and it's not so easy to handle. But then it works still. So this can be. But secondly, examples show especially the harmonic oscillator, which I wanted to explain here, but I think it's too long. And examples show there is a shift in eigenvalues. I mean, it's already quite interesting that you get really good examples, but there's a shift in eigenvalues, which is not easy to handle. I mentioned the third stage. This is so-called half-form correction. What we do is, instead of L, we find an S. We replace L by a new line bundle, and S is a square root of the so-called canonical bundle of P. I'm sorry, or of P, or the dual of P, but it doesn't matter really. So what you had to have a square root of a vector bundle, of a line bundle. This is similar to the situation of a spin structure in general Riemannian geometry, and the replacement works through, and the shifts in eigenvalues are perhaps so that the next step I should perhaps just mention. I mean, this is already a rather complete picture, and it was more or less finished in the 80s. And since then, one has in the fourth stage. Yeah, what is the reason? 2 minutes, okay? The fourth stage. What can happen? Bad things can happen. Everything is nice, and this gamma ML is 0. For example, in Kähler manifolds, if you have line bundles, and you have the automorphic polarization, when you need complex sections, and very many line bundles have no complex sections. So the other thing is R can be 0 or only constants, in the sense that everything works only for constants. That's also not very interesting. And the third thing is what I forgot to mention is that is odd, because this condition is in the same way as in the case of spin structures is exactly this condition. So these 3 things go wrong. So we have to have variance, and let me say what can be done. For example, here one can, instead of L, the sections, one could start all cohomology classes. This is already suggested by Kähler manifolds, you can say. Or here, what can be done is you change the Q. The Q is nice, but you can also say Q is somehow F plus some constant C1 of what we have called Q. So this is the new Q. Plus, here we add some Q n or k of f from 2 to infinity or some n, whatever you want to. So you can change the Q, and this way one can make many more R's to be quantizable. And the last thing here, you can also change the condition in the sense one that is, for example, a so-called MP seal. And we have the metapletic, if we have this situation, we have a metapletic structure, and this is a more general group, which is essentially the extension of the metapletic group by Q1. And if you do this, then you get a more general condition than this condition, and this includes, for example, the P-ends. And then I stop. Okay, all the KISS stage is do this thing, everything on fields, but nobody has really done it, so that you get a quantum field theory at the end. Thank you.
For good questions, maybe. Over there on the right hand, the pocket is on each, and what is Asian is this? This Q maps from sections to object on these. The Hilbert space. What do you see?
You didn't.
Yeah, I'm a bit.
The problem.
What is the Hilbert space H in this case? This third one?
In this case.
Yeah. So I think.
Yeah, that's. I was a bit too fast at this drawing. It's. You have the sections. Okay, the tree-Hilbert space consists of S of gamma delta, such that the integral of the Hermitian structure of the section with the cell d omega n is smaller than infinity. So you take more or less in the most natural structure you have. This is good because you are omega n, but you touch a very important point. This is not so easy to do if you have a polarization. Then one has to work a bit to get a reasonable measure on a certain quotient space of the shape.
So can I ask if self-adjointness of the resulting operator is dramatic?
It is dramatic, yeah.
Okay.
I didn't want to go into this detail. It's always dramatic, I think, in physics. If you have a model, then you have finally, after everything has begun, you still have to figure out what it is. Self-adjoint. What happens is it's formally self-adjoint. We have essentially defined, and it's symmetric, and so it has a good chance. But there are examples where it is not the case. It is always the case that the original manifold M is compact. Then you get automatically say Martin's.
All right. Well, let's thank Martin again.